In this video, we present a novel approach for automatic targetless camera-LiDAR calibration by using sensor motion and deep learning-based point correspondences. Sensor fusion of camera and LiDAR aims to efficiently combine complementary measurements from different modalities. Therefore, these sensors are commonly installed jointly in robotic applications, such as autonomous driving. This combination can not only enhance the overall performance of the perception system, but also increase its general robustness. However, the effectiveness of sensor fusion approaches heavily relies on accurate extrinsic calibration. Existing calibration techniques can generally be classified into target-based and target-less methods. Target-based approaches often rely on artificial patterns, such as checkerboards or 3D structures, rendering specific data collection necessary. Although some effort has gone into automating the detection of key points of these objects, the majority of methods still rely on manually selected point correspondences between images and point clouds. Often, the transfer between the sensors is then obtained via ICP or PNP algorithms. On the other hand, some targetless methods replace these artificial targets with patterns present in structured environments, such as semantic edges. Another conceptually simple idea is generating structure from motion maps from camera data that can be matched with LiDAR point clouds to find the 3D transformation between both sensors. Further approaches include exploiting auxiliary tasks, such as matching sensor motion, or more recently, directly estimating their parameters by leveraging deep learning. In conclusion, due to the absence of specific calibration targets and decreased human supervision, targetless methods enable more flexible and more scalable calibration. However, most methods still require an initial guess at the parameters. In this work, we explicitly address such shortcomings. In particular, we propose to combine sensor motion estimates with deep learning-based point correspondences in a two-stage graph optimization approach. A strong advantage of this work over previous targetless learning-based approaches is that our method requires neither any initial parameters nor retraining for different sensor configurations. We interpret camera-to-LiDAR calibration as a mathematical optimization problem that aims to determine the most probable calibration parameters given a set of sensor measurements. This yields a conditional probability distribution for which we can obtain a maximum a priori estimate by minimizing the cost function j. In our approach, we decompose this function to two separate terms for sensor motion and image-to-point cloud correspondences. In stage 1, we perform coarse calibration by matching sensor motion. We estimate the camera poses with the visual odometry method OBSPIM3. For the LiDAR, we utilize a customized version of FastLeo2, where we remove the IMU requirement. Assuming that both sensors are time synchronized, we can then interpolate the estimated poses and match relative sensor motion. These matches induce constraints in a vector graph. Finally, we perform graph optimization to obtain our initial set of calibration parameters. In the second stage, we process synchronized pairs of point clouds and images. In detail, given a 3D LiDAR point, known camera intrinsics, and the initial extrinsic calibration parameters, we can now use 3D to 2D projection to estimate the corresponding pixel in the 2D image domain. Now we leverage a correction from the deep learning-based CMR-Next to refine the point correspondence. Separately, we can set up an equation for the direct projection of the 3D point to this corrected 2D pixel, where the extrinsic parameters pose an unknown variable. This equation can hence be added as an additional constraint to our vector graph. We repeat this procedure for multiple points within the same as well as from further point cloud image pairs. In the end, graph optimization produces a final set of calibration parameters. We first evaluate our method on sequence 0 of the KITTI dataset. In comparison to the purely learning-based LCCNet, we achieve smaller calibration errors. However, it is paramount to keep in mind that the training of both LCCNet and the utilized CMR-Next was, at least partly, based on the left camera of other KITTI sequences. Therefore, we next employ both methods to the right camera, demonstrating that LCCNet does not generalize to other sensor setups. In our paper, we show that most learning-based methods suffer from this problem. In contrast, our approach yields highly accurate results, even on unseen configurations. In this video, we project the LiDAR point cloud onto the images of the right camera. As visible in the zoomed-in area, our obtained calibration is accurate also for distances of approximately 60 meters. Turns are another challenging scenario and often reveal inaccuracies in the calibration parameters. In this final example, please pay attention to the correct projection of the dark blue points on the trees that are up to 80 meters away. Finally, we showcase the general applicability of our method to various robotic platforms. Note that our method does not require any kind of retraining as long as the utilized sensor measurements roughly match the domain of urban scenarios. We show sensor configuration for a passenger vehicle, a quadruped robot, and a UAV. Similar to the results for Kitty, we obtain accurate predictions even for very far away objects. In conclusion, we proposed a new method for automatic targetless calibration between camera and LiDAR sensors. Our approach does neither require any initial parameters nor retraining for different setups. Although we do use deep learning, we relax its black box nature by leveraging the estimated point correspondences in a classical optimization setup. Please visit our project website for further information, including the code and detailed instructions for calibrating your sensor setup. Thank you for your attention.